All right, ever find yourself staring at a hot frying pan, maybe making pancakes or something, and just wondering, like, hmm, how much faster are those little air molecules zipping around up there compared to just the regular air in the kitchen?
Huh. I'll admit I haven't thought about that specific scenario, but you've definitely piqued my curiosity. It's a surprisingly profound question when you think about it.
Yeah, I mean, if the pan's at like 100 degrees Celsius and the room's at 25, are those molecules like twice as fast, four times as fast? What do you think?
Honestly, our intuition can be pretty misleading when it comes to the microscopic world. But that's exactly the kind of question we're going to tackle in this deep dive. We're going to journey into the invisible realm of gas molecules and uncover the often mind-boggling rules that govern their behavior. We'll unpack those fundamental concepts you mentioned, temperature, pressure, molecular motion, and really reveal that hidden link between the everyday world we see and feel and the frenetic activity of trillions upon trillions of molecules.
Love it. And to help guide our exploration, we've got some fantastic source material here, diving deep into the thermal properties of matter. We're talking about equations that describe how gases behave, this thing called the kinetic-molecular model that explains it all from the ground up, the whole concept of heat capacities, and even how the speeds of these tiny particles are distributed. Don't worry, we're not aiming for a physics lecture here. We'll distill the most mind-bending and crucial insights so you come away with a solid understanding of what's happening at the molecular level without feeling overwhelmed.
Right? We want to spark that curiosity, that aha moment, not drown anyone in equations.
Yeah, exactly. Our mission, if you will, is to grasp how temperature really dictates the behavior of these gas molecules, and as a result, how that impacts the macroscopic properties of gases that we actually experience. So by the end of this, that frying pan mystery will be solved, but you'll also have a whole new appreciation for the physics happening all around us, constantly.
I'm all for that. So to kick things off, let's just lay down a fundamental idea. We can understand the world through these two very different lenses, the macroscopic and the microscopic. On the one hand, we have the big picture stuff, pressure in your car tires, the volume of air in a balloon, the temperature outside those are what we call macroscopic properties. But beneath the surface, there's this whole hidden universe of individual molecules, each with its own minuscule mass, zipping around with incredible velocity, each carrying its own little packet of kinetic energy.
And here's the crazy part, those two perspectives are completely intertwined.
Yeah, absolutely. It's mind-blowing when you think about it.
Like, take something as simple as atmospheric pressure, right? We feel this constant force pushing down on us from the air above. But what's the actual source of that force at the microscopic level?
It's those countless air molecules constantly bombarding our skin and every other surface. And get this, on average, roughly 10 to the power of 32 of those molecules strike your body every single day.
10 to the power of 32, that's...
It's an astronomical number. And they're not just gently bumping into us. They're traveling at insane speeds, exceeding 1,700 kilometers per hour on average. That's way faster than a speeding bullet.
Wow. So even though everything feels still, there's this constant, incredibly intense molecular storm happening at the microscopic level.
Precisely. It's mind-boggling. Now, when scientists want to get a handle on the behavior of gases, they often start with this concept of an ideal gas. It's essentially a simplified model that helps us understand the fundamental relationships between pressure, volume, and temperature.
So it's kind of a theoretical gas, but it helps lay the groundwork, right?
Exactly. In an ideal gas, we imagine the molecules as these tiny points that have mass but essentially no volume of their own. And crucially, they don't exert any attractive or repulsive forces on each other.
Oh, so they're just kind of like bouncing around freely, totally independent.
Yeah, that's the idea. And when they collide with each other or with the walls of their container, those collisions are perfectly elastic, meaning no kinetic energy is lost in the process. It's a clean, basic picture that allows us to build our understanding.
And I'm guessing this ideal gas behavior is captured by a pretty important equation.
You guessed it. It's one of the most famous equations in physics. The ideal gas law. You might have seen it written as PV equals nRT.
Yeah, I vaguely remember that from high school chemistry. Refresh my memory, though. What do all those letters stand for again?
No problem.
Mm-hmm.
So P represents the absolute pressure of the gas. That's the total pressure, not just the pressure relative to the atmosphere. V is the volume it occupies. N is the number of moles of gas we have, which is just a way of measuring the amount of substance. R is the ideal gas constant, a fundamental constant in physics, with the same value for all ideal gases. And T is the absolute temperature measured in Kelvin. Using absolute pressure, and Kelvin is non-negotiable here.
Okay, so absolute pressure and Kelvin, got it. Now, if we have a fixed amount of an ideal gas trapped in a container and we change one of these properties, like we squeeze the container to reduce its volume, what happens to the other properties? Do they change in a predictable way?
Exactly. For a fixed amount of gas, the ratio of pressure times volume divided by temperature remains constant. This leads to a very handy equation when we're comparing two different states of the same gas. P1V1 divided by T1 equals P2V2 divided by T2. So if we change the pressure, volume, or temperature, we can use this equation to figure out how the other two properties will change.
And this isn't just theoretical, right? The source material gives a pretty cool real-world example of this in action, the compression stroke in an internal combustion engine.
Yeah, that's a perfect illustration. So picture this. You've got air and fuel vapor mixed together in the cylinder of your car engine. Initially, it's at a certain pressure, volume, and temperature. But when the piston moves up, it compresses that gas mixture, reducing the volume drastically. And because of that relationship we just talked about, both the pressure and the temperature shoot way up. In fact, the source material even gives us specific numbers. If the volume is reduced to 1/9 of its original size, starting at 27 degrees Celsius and 1 atmosphere of pressure, the final pressure jumps to over 21 atmospheres, and the temperature skyrockets to 450 degrees Celsius. That's hot enough to ignite the fuel and power the engine.
Wow, that's pretty incredible. A seemingly simple compression leading to such a drastic change in temperature and pressure, all because of that fundamental gas law.
Right, the physics of play is powerful. Now, let's talk about another important property of gases, density. How much mass is packed into a given volume?
Right, so basically how heavy the gas is for a certain amount of space it takes up.
Exactly. For an ideal gas, the density, represented by the Greek letter rho, can be expressed in terms of pressure, molar mass, the gas constant, and absolute temperature. The equation is rho equals pressure times molar mass divided by the gas constant times absolute temperature. So again, if we know some of these properties, like the pressure and temperature of the gas, and we know what type of gas it is, so we know its molar mass, we can easily calculate its density.
Okay, so we've got a handle on these big picture properties. Pressure, volume, temperature, density, and how they all relate to each other in an ideal gas. But let's zoom back in now to those individual molecules and really get a feel for what's happening at that microscopic level. The source material introduces the kinetic-molecular model. What's the gist of this model?
Well, it's all about explaining those macroscopic properties we just talked about from the ground up, based on the behavior of individual molecules. It's based on a few key ideas. First, we imagine a gas as a huge number of tiny molecules, each with a specific mass.
Like billions and billions of them, right?
Way more than billions. Think trillions upon trillions. Anyway, the second key idea is that we treat these molecules as point particles. Their size is so small compared to the distances between them that we can essentially ignore their volume. Third, these molecules are in constant random motion, constantly bouncing off each other and the walls of their container. And finally, these collisions are perfectly elastic. So when molecules collide, they don't lose any kinetic energy. They just bounce off each other like perfectly bouncy rubber balls.
So how does all this constant motion and collision at the microscopic level create the pressure that we measure at the macroscopic level?
It's all about those collisions with the walls of the container. Each individual collision exerts a tiny force on the wall. But because there are so many molecules and they're colliding so frequently, trillions of times per second, the cumulative effect of all those tiny impacts creates the pressure we observe. And the kinetic molecular model lets us actually put this into a mathematical equation that relates the pressure and volume to the number of molecules, their mass, and their average speed.
Okay, that makes sense. More collisions, more force, higher pressure.
Yeah.
Now, how does temperature fit into this microscopic picture?
This is where things get really elegant. Remember that equation we talked about earlier, the ideal gas law? PV equals nRT. Well, by combining that with the equation from the kinetic molecular model, we can actually link the macroscopic property of temperature directly to the microscopic kinetic energy of the molecules. It turns out that the average translational kinetic energy of an ideal gas is directly proportional to its absolute temperature. The hotter the gas, the faster its molecules are moving on average, the higher their kinetic energy.
So basically, temperature is a measure of how much those little molecules are jiggling and zipping around.
Exactly. The more they're jiggling, the hotter the gas. Now, here's a question for you. Do you think all the molecules in a gas at a certain temperature have the exact same kinetic energy and therefore the same speed?
I'm going to guess no, just based on how random everything seems to be at that level.
You're absolutely right. While the average kinetic energy is determined by the temperature, The individual molecules have a wide range of speeds. Some are moving super fast, some are moving slower, but the average kinetic energy is what's linked to temperature.
So how do we even begin to describe that range of speeds?
That's where something called the Maxwell-Boltzmann distribution comes in. It's basically a probability distribution that tells us what fraction of the molecules are moving at different speeds at a given temperature. It turns out it's not a symmetrical distribution. More molecules are moving at speeds close to the average, but there's a long tail of molecules moving much faster. And importantly, as the temperature increases, this entire distribution shifts towards higher speeds.
So even if the average speed increases a certain amount, there are now way more molecules moving at those super high speeds.
Precisely. And that can have a huge impact on various processes, like the rate of chemical reactions or the evaporation of liquids. But let's not get sidetracked. We were talking about how individual molecules have different kinetic energies. Now, here's a really fascinating point. At a given temperature, the average kinetic energy of a molecule only depends on the temperature, not on the molecule's mass.
So a really light molecule and a really heavy molecule at the same temperature will have the same average kinetic energy. How does that work?
It seems counterintuitive, right? But remember, kinetic energy is determined by both mass and speed. So if a lighter molecule and a heavier molecule have the same kinetic energy, the lighter one must be moving faster on average to compensate for its smaller mass.
That makes sense. So I'm guessing there's a way to calculate this average speed we keep talking about.
Yes, there is. It's called the root mean square speed, or VRMs for short. It's essentially a way to characterize the typical speed of the molecules in a gas. And the formula for VRMs shows us that at a given temperature, lighter molecules will have a higher VRMs than heavier ones.
Which explains why nitrogen molecules in the air tend to move a bit faster on average than the slightly heavier oxygen molecules, right?
That's exactly right. And it also explains why lighter gases like hydrogen can escape from Earth's atmosphere more easily. Their higher average speeds mean they're more likely to reach escape velocity and just zoom off into space.
Okay, so we've laid a lot of groundwork here, but let's go back to that frying pan question that started this whole thing. How much faster are the air molecules above that sizzling pan at 100 degrees Celsius compared to the air in the kitchen at, say, 25 degrees?
All right, let's do the math. Remember, the ratio of the VRMs values at two different temperatures is equal to the square root of the ratio of those temperatures in Kelvin. So in this case, we're looking at the square root of 373 Kelvin divided by 298 Kelvin.
And what does that give us?
It works out to be about 1.12.
So the air molecules above the 100-degree pan are only about 12% faster on average. That's way less than I would have guessed. I was thinking like twice as fast, maybe even more.
Yeah, our intuition can be really off when it comes to these things. Our brains aren't wired to think in terms of square roots and absolute temperatures. But it's a good reminder that even a seemingly large difference in temperature doesn't necessarily translate to a huge difference in molecular speed.
All right, let's move on to another fascinating concept that the source material delves into: heat capacities. Now, I remember from chemistry class that different substances have different capacities to absorb and store heat, but how does the kinetic molecular model help us understand that?
Well, think about it this way. Heat capacity is essentially a measure of how much energy you need to pump into a substance to raise its temperature by a certain amount.
Right, so some substances need more energy than others to get hotter.
Exactly. Now, the molar heat capacity at constant volume, denoted as CV, tells us how much heat we need to add to 1 mole of a substance to raise its temperature by 1 Kelvin without changing its volume. And the kinetic molecular model gives us a really neat way to understand how this works at the molecular level.
Okay, I'm all ears.
So for a simple monatomic gas like helium or argon, the only way those single atoms can store energy is through their translational kinetic energy, that is, the energy associated with their movement through space.
So they can zip around faster, but that's pretty much it?
Right. They don't have any internal structure to store energy in other ways. And because of that, their molar heat capacity at constant volume is directly related to the gas constant R. It turns out to be 3/2 times R. And what's amazing is that this theoretical prediction matches really well with the experimental measurements for these monatomic gases.
So the model seems to be working pretty well so far. But what about more complex molecules, like diatomic molecules like nitrogen and oxygen, or even larger polyatomic molecules?
That's where things get a bit more interesting. These molecules have more ways to store energy than just translation. Diatomic molecules, for instance, can also rotate, like a dumbbell spinning end over end. And both diatomic and polyatomic molecules can vibrate, with the bonds between their atoms stretching and compressing like little springs.
So it's like they have more internal wiggle room to store energy.
Precisely. And each of these different ways a molecule can store energy is called a degree of freedom. The more degrees of freedom a molecule has, the more energy it can absorb for a given temperature increase.
So diatomic molecules, with their ability to rotate, would have a higher heat capacity than monatomic molecules.
Exactly. And polyatomic molecules, which can have even more vibrational modes, have even higher heat capacities. There's this principle called the equipartition of energy that says each active degree of freedom contributes a certain amount of energy to the molecule's total energy. So the more ways a molecule can move and jiggle, the more energy it takes to raise its temperature.
Okay, that makes perfect sense. Now, the source material mentions something interesting about these vibrational degrees of freedom. Apparently, they can sometimes be frozen out at lower temperatures. What's that all about?
That's a great question. So it turns out that the energy associated with molecular vibrations isn't continuous. It comes in discrete packets or quanta. And for some molecules, the energy difference between the lowest vibrational state and the next higher one can be pretty large.
So if the molecule doesn't have enough energy to make that jump to the next vibrational state, it can't really absorb energy in that way.
Exactly. If the available thermal energy, which is related to the temperature, is much smaller than this energy gap, those vibrational degrees of freedom are essentially inactive. They're frozen out. It's only when the temperature gets high enough that those vibrational modes can start absorbing energy and contributing to the heat capacity.
So it's like the molecule needs a certain amount of energy to unlock those vibrational modes.
That's a great analogy. Now let's shift gears a bit and revisit that idea of molecular speeds. We've talked about average speeds, but we know that not all molecules are moving at the same speed. Some are slower, some are faster. How do we account for that distribution of speeds?
That's where the Maxwell-Boltzmann distribution comes back in. It describes the statistical spread of speeds within a gas at a particular temperature, and it turns out it's not a symmetrical distribution.
Right. It's not like a perfect bell curve where the average speed is the most common one. There's actually a longer tail of molecules moving at much higher speeds.
So even at a relatively low temperature, there's still a small fraction of molecules zipping around super fast, and as the temperature goes up, that fraction increases, right?
Exactly. And that has important implications for things like evaporation and chemical reactions. Even at temperatures below a liquid's boiling point, some of those faster-moving molecules at the surface have enough energy to escape into the gas phase. And in chemical reactions, only the molecules with enough energy can overcome the activation energy barrier and actually react. So that high-speed tail, the Maxwell-Boltzmann distribution, plays a crucial role.
So we've covered a lot of ground here, from the ideal gas law to the intricacies of molecular motion. But there's one more concept from our outline that I want to touch on. The mean free path. What is that exactly?
It's a measure of how far, on average, a molecule can travel through a gas before bumping into another molecule. It's a key concept for understanding things like diffusion and the transfer of heat through a gas.
Right, so the more crowded the gas is, or the bigger the molecules themselves are, the shorter that mean free path will be.
Exactly. The source material provides a formula for calculating the mean free path. And it depends on the volume of the gas, the size of the molecules, and the number of molecules. And surprisingly, the average speed of the molecules doesn't directly affect the mean free path.
Wait, why not? I would think that a faster molecule would travel farther before hitting something.
Well, a faster molecule does cover more ground in a given time, but it also encounters and collides with more molecules during that same time. Those two effects basically cancel each other out.
Okay, so it's like a crowded highway. Even if you're driving faster, you're still going to run into more cars if there are more cars on the road.
That's a great analogy. Now, here's another interesting point. The mean free path can change with temperature and pressure. If we increase the temperature while keeping the pressure constant, the gas expands, the molecules are farther apart, and the mean free path increases. Conversely, if we increase the pressure at a constant temperature, the gas gets compressed, the molecules are closer together, and the mean free path decreases.
So it's all about how densely packed the molecules are.
Precisely. And the source material even gives us an example calculation for air molecules at standard temperature and pressure. The mean free path is incredibly tiny, only about 58 nanometers. That means each air molecule is colliding with others billions of times every second.
Wow, it's mind-boggling to think about all those collisions happening constantly in what seems like empty space to us.
Yeah.
Okay, one last thing from our outline that I want to touch on. The different phases of matter, solid, liquid, and gas. How does all this talk about molecular motion relate to those different states?
It all comes down to the interplay between the kinetic energy of the molecules and the intermolecular forces between them. In gases, the kinetic energy dominates. The molecules are moving too fast and are too far apart for those intermolecular forces to hold them together, so they spread out to fill whatever space they're in.
They're basically just bouncing around freely.
Yeah, pretty much.
Yeah.
In liquids, those intermolecular forces start to play a bigger role. The molecules are closer together and moving a bit slower, so they can stick together a bit more. That's why liquids have a defined volume but can still flow and change shape.
So the molecules can move around each other, but are still kind of clinging together.
Exactly. And in solids, those intermolecular forces are really strong. The kinetic energy is much lower, so the molecules are essentially locked in place, vibrating around fixed positions in a crystal lattice.
So they're basically stuck, but still wiggling a bit.
Right. And of course, we can transition between these phases by changing the temperature or pressure, which alters the balance between kinetic energy and intermolecular forces. The source material mentions PVT surfaces and phase diagrams, which are graphical ways of showing the conditions under which different phases can exist. And these diagrams are super useful for understanding things like why water can't exist as a liquid on Mars because the atmospheric pressure is too low.
Wow, that's amazing how all this ties together. All right, just to recap some of the key things we've learned today. We saw how temperature directly relates to the average kinetic energy of those constantly moving gas molecules, how those collisions create pressure, how the speeds of the molecules are distributed, and how the structure of a molecule affects its ability to store energy.
Don't forget the mind-blowing fact that those air molecules are bouncing around at over 1,700 kilometers per hour.
Right. And we solved that initial frying pan mystery. Turns out those molecules are only about 12% faster over the hot pan. So our intuition can be way off when thinking about these things.
Yeah, it's a good reminder that the world at the microscopic level could be very different from what we experience in our everyday lives.
And these principles we've talked about today, they're not just theoretical curiosities. They're fundamental to understanding so many things, from how engines work to how weather patterns form to how we cook our food.
Absolutely. So here's a final thought for you all to ponder. If the air molecules around us are constantly moving at hundreds of meters per second, why don't we feel a constant, powerful wind? It's a great question to mull over, and it might lead you down some fascinating rabbit holes of statistical mechanics and thermodynamics if you're curious to explore further.
Well, I think we've given our listeners plenty to think about today. Thanks for joining me on this deep dive.
It's been a pleasure.
Yeah.
Until next time.